Hello and welcome to the first ever YouTube video on the Actuate YouTube channel. My name is Mike Cavalier and I'm very proud and grateful to be able to call myself the founder and CEO of this little company that my friends and I have decided to start together. In addition to creating online tutorial videos, one of which you are viewing right now, we provide free tutoring for probability and financial mathematics. We're geared towards tutoring this towards the Society of Actuaries exams. However, if you're having any trouble with financial mathematics or probability coursework, please feel free to view the website link that is most likely going to be at the top of the description of this YouTube video. We are ready, willing, and able to help you in any area of these two subjects. Today, our version of help is going to be in the form of combinatorics. It's the bread and butter of pretty much anything probability related in whatever sort of way you're studying it in, whether it's for actuarial exams or just general mathematical statistic coursework. Probability is defined and is based on combinatorics. So I have a few examples that we're going to go through today to showcase all of the different combinatoric techniques, mainly combinations and permutations that would come up in questions related to any of these fields. So I decided to, for our first example, go with something that is actually pretty applicable to my own life and this company. So although the numbers are a little bit different, the concept is still the same, and this is how you would calculate the probability of it. So Actuate is hiring, and they're looking to fill 3 positions: COO, CFO, and CAO. If they received 10 applications in which all applicants were interested in all 3 positions, with preference order of COO, CFO, and CAO, this will be important in a little bit, how many unique groupings can be created? So the question is essentially asking us how many different ways can these 3 positions be given out to a group of 10 people if they have a preference of COO, then CFO, and then finally CAO. So I think the most simple way to go about this is to just start by drawing 3 lines. And the significance of these lines is I'm going to label each of them by a respective position. So COO, CFO, and then finally CAO is what I'm going to be listing all of these lines and spaces as. I'm going to write down just some information just so I don't get lost. There's 10 people who applied. The preference order, so I'll just say P order, is COO, then CFO, and finally CAO. And then, there has to be a grouping of 3 people. So let's get started. I'm going to look at this COO square first. It's the first thing on everyone's preference list, and there were 10 people applying. So essentially, there is 10 different outcomes for how this situation can happen. If you have people listed person 1 through 10, person 1 could get it, person 2 could get it, person 3 can get it, all the way down to person 10. So I'm going to put 10 here, and I'm going to leave that for a little bit. Moving on to CFO. We're going to operate under the assumption that someone already got the COO position. They're already the vice president of Actuate. All of the people that were interested in applying said they're interested in all 3 positions, and if COO isn't available, their new most desired position is CFO. And there's 9 people who are still interested in this position, of which there's 9 different outcomes. So pausing there for a little bit, neglecting CAO entirely for the moment, want to think about what's happening right now. We have 10 people who were interested in COO, 1 person got it, and then there are now 9 people interested in the CFO position because 1 person already got COO, and they're now no longer interested in any of the subsequent positions because they already have one of their own. Out of this, there's now 90 different possibilities, and that's a big number, and I don't have a calculator on me. So how did I calculate this? I just did some multiplication, but the reason why the multiplication is important is this. If we have 10 different people, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and they're all interested in the COO position. If they get it, there's now 9 different ways that the rest of the positions, or in this case, just the one position, could be allotted. It could go to 9 different people. So I'm only going to write it out for one, but the same applies for all of them. If one gets the first position, then 2 through 10 are eligible to get the second position, and the same would go true down the line. The only difference being if 2 got the position, then it would be 1, 3, 4, 5, 6, 7, 8, 9, and 10 who are available for the second position. So going back to our initial sort of thought process, if 10 people got COO and then 9 people were still interested in CFO, finally 8 people would be interested in the final position, CAO. If we were continuing to branch out on this tree that we had earlier, say 1 got COO, then 2 got CFO, then 3, 4, 5, 6, 7, 8, 9, and 10 would be eligible for CAO. And you can go down the line for any singular one of these and determine, honestly, just by counting, how many different ways this executive board essentially could be assembled. But this right here is only one way that the 3 positions could be given out, and there are a lot of ways that these 3 positions could be given out. The way that we calculate this is just by multiplication. These are independent events, which means you could multiply them by each other to find the total amount of different ways that these positions could be grouped, and the results of this multiplication sees that there are 720 different ways that these positions could be given out. To put a formula on this and to put a term on this, what we just did is called a permutation. That's a big buzzword in the world of probability, and it's denoted by something like this. We have a variable n with a big P and then a little r. We're just saying that n is the total amount that we're choosing. In this case, it was 10, and r is the amount that we're permuting by. So in this case, 3, since there were 3 different positions. The formula for this is a very, very simple formula. All that we're going to do here is take n, basically make it a factorial. So 10 factorial in this case, and divide it by n minus r factorial. That is the formula for a permutation, and using the numbers above, we would have 10 factorial divided by 10 minus 3 factorial, which is 10 factorial over 7 factorial, and doing the math out, what we get is just 10 times 9 times 8, which is equal to the same 720 that we got before. I'll show you when to use the permutation in a little bit. This is one example of which it can be used, but first I want to show you an example where it could not be used. And what we're going to use in this example is a combination. So example 2 says that Actuate still has 3 more positions to fill, of which now a different set of 10 people, so completely different people from the first example, they applied for it. These positions require the employees to do equal amounts of work and are indistinguishable from each other. How many unique groups of 3 can now be created? Seems pretty similar rather, than the first example, and it would definitely make sense to apply the same similar thought process from the previous example to solve. And while I'm naming this position 1, I'm naming this position 2, and I'm naming this position 3, these are essentially all the same thing. Position 1 is going to be doing the same work as position 3, just as position 3 is going to be doing the same work as position 2. They're all indistinguishable from each other. I'm simply distinguishing this just to make a point. We have, yet again, 10 people that are applying for these positions. There are 3 positions, and just to say this again, positions are indistinguishable rather, from each other. I really hope I didn't make a spelling mistake there. That might be an I. Not too sure. I'm a mathematician. I don't need to know how to spell, I think. If you have position 1, there is still going to be 10 people who are interested in it. If you look at position 2, if one person got position 1, there are now 9 people who are interested in the second position, and if 2 people got position 1 and 2, 8 people are interested in that third position. And if we multiply these out, we would actually get the same 720 as we got in the example prior. But now, as an educator, I am going to raise a question. Is there a difference in this problem from the last one? And since I'm showing this as a second example, for the purpose of the video, yes, there is. But why? And the answer lies in just taking an individual grouping, and I'm going to analyze what happens, and we're sort of going to see why these cases are different. So let's say we have person 1, person 2, and person 3. And these people are part of the set of 10 people who applied. Part of set of 10, I'm going to write. And let's say that we allot the positions to these 3 people. Position 1 is given to person 1. Position 2 is given to person 2. And position 3 is given to person 3. It seems like a reasonable way to allot the positions, and it absolutely is. But what if I say that I'm going to give position 1 to person 3? I'm going to give position 2 to person 1. I'm going to give position 3 to person 2. If these positions are all doing the same amount of work and they're not named and they're not able to be distinguished from each other, is there really a difference here? No. These people are working as a team of 3. They're being combined together out of the big set as they have been chosen to work on this team together. And this is a very, very interesting concept because there are a lot more than just 2 different ways to organize these positions. In fact, there's actually 6. And it's likely something that has come up in a very simple math class, maybe in middle school or early high school. To put this in a vacuum, say we have letters A, B, and C, and I ask how many different ways could we arrange these letters? And naturally you would go A, B, C, then you would go A, C, B, you would go B, A, C, B, C, A, C, A, B, and C, B, A, to get a total of 6 ways you could organize these 3 letters. And it's the same exact concept that could be put back to this here. We have person 1, 2, and 3, and they're all going to be on a team together, but they're going to be doing 3 separate positions. And you could list this as 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. There's 6 different ways that you could organize them, but they're all in the context of this problem actually the same. Because they're all on that same team of 3, they're all doing the same work, the positions are nameless, they can't be distinguished from each other. So we actually have to divide a permutation by something new, and in doing that, we achieve the combination. So why am I dividing? I'm going to erase this for the moment, just to free up some space for myself without exposing the final problem of this video. We said that 10 permutation 3 is equal to 720, which is equal to 10 factorial over 7 factorial. What we need to do is actually divide this by a factor of 6, because for each way that you could assemble a team of 3, we're actually overcounting it by a factor of 6, because each group of 3 can be arranged in 6 different ways, but The way in which they're ordered, the way in which they're arranged is really just not important, or shouldn't be counted in the context of this problem, since 1, 2, 3 is essentially the same as 3, 2, 1. So we're going to divide by 6. But there's a significance to this number. It's actually 3 factorial, which is a pretty simple calculation, but why? Why is it important? Why is that the factor that we're dividing by to make our new answer 120 instead of 720? And it lies in the formula of a combination. We're, in the context of this problem, being asked to find unique groups of 3, but they're all doing the same work and the positions aren't defined, so we're combining a group of 3 out of the set of 10 to make a team. And unique groupings, in terms of this problem, requires you to do a combination. The formula here, denoted by 10C3, or rather NCR, can be defined like so. We're going to have n factorial on the top, and on the bottom we're actually going to still have that same n minus r factorial, but we're going to multiply that now by r factorial. The r factorial is going to be able to account for the amount of times that we overcounted, since this is now a combination where order does not matter, as opposed to a permutation where order indeed does matter. So this could actually be written as NCR is equal to NPR divided by R factorial. Pretty interesting stuff. And in the context of this problem, 10C3, which I'm just bringing down from here, is equal to 10 factorial divided by 10 minus 3 factorial times the subsequent 3 factorial. It's going to give us something a little bit like this, which could be rewritten as this, which is equal to this. And that is a combination. So what's the difference? Why are we using a combination here? Why are we using a permutation there? It's a very valid question. It's the question that I was asking myself when I was learning this for the first time, and the answer lies right here. In a permutation where the positions were named, right, we had a COO, we had a CFO, and we had a CAO, the way in which the people were ordered mattered. In this case, it doesn't. ABC, BCA, ACB, however we're being asked to combine these, whether it's in numbers, letters, stars, squares, doesn't matter, you name it. In a combination format, in a combination style question, the order does not matter, but in a permutation style question, it does. The sort of buzzwords, right, you could be like, how can these people be combined? What a carrot. If they ask for a combination, you do that. If they ask for a permutation, you do a permutation. It's all in the wording of the question, but it sort of goes back to just these 3 lines, multiplying them out since they're independent events, and choosing the right formula for the right question. And with practice and with overclocking your minds with a lot of problems, the answers and, well, the tool in the bag of tricks that you have to apply, it starts jumping out to you. And it's a really, really cool thing once it does start to happen, because then you get questions like this, where, well, I'm going to read the question out, but we're going to see that a combination or a permutation actually isn't applicable here. And I'll show you why. So in the final example, Actuate has an opening for 3 more positions, of which a third group of 10 people have applied for. If these positions are indistinguishable from each other and multiple positions can be held by 1 employee, how many different ways can these positions be filled? So very similar wording yet again for a third time. However, there are some key differences which can be shown in 3 lines. It's a pretty big line. I think I'm going to draw that one a little bit smaller. All right. So Yet again, we have three positions, position 1, position 2, and position 3. And while I'm naming them, they're all actually the same thing. They can't be distinguished from each other, but in solving this problem, we are temporarily. We still have 10 people, we still have 3 positions. However, I'm going to say indistinguishable. Now, multiple positions can be held by one person. So, what changes here? In the first line, absolutely nothing. Using the same logic as we had before, we have 10 people that could be put in the first slot, since 10 people applied for these set of 3 positions. But going to position 2, what's going on here? Multiple people can hold the same position. You could hold 1 position, no positions, 2 positions, or 3 positions. That's the outcome for every applicant here. If 10 people could hold position 1 and position 2 could be held by the same person who held position 1, and no people are sort of being denied a position here, the chance to have one, 10 people could hold position 2, and by the same logic, 10 people, 10 different outcomes of people could hold position 3. The events are all independent from each other, which means we can multiply them out, and we actually see that there are 1,000 different ways that these positions could be filled. There are 1,000 different unique combinations of people that could fill these positions. It can't be calculated through a combination because a permutation rather, because the order doesn't matter, but it also cannot be solved through a combination since multiple people could hold the same position and you're not just combining a group of people out of the larger set into these 3 positions. So that's all I have for this video. We've gone over permutations, we've gone over combinations, and we've gone over an example where neither of the two could be applied, and we're really just counting the different ways that these positions could be filled. If you made it this far, thank you so much for making it to the end of the first ever Actuate YouTube video. I appreciate it. The link will be in the description if you are interested in having myself or one of my fellow employees give you tutoring for no price, no cost at all, and see you in the next video.